Okay. Uh, Good morning, everyone. My name is Fabio Roli, and it is indeed a great pleasure and honor for me opening this scientific workshop on the future of AI in academic research with a focus on machine learning, quantum computing, and cybersecurity. First of all, let me really thank the organizer of this event, Professor Roberto Giuntini, all the other colleagues, and all the distinguished colleagues and friends who are here today. But my role today is just opening this event, and then I leave the floor for the institutional speeches to other distinguished colleagues. So I'm asking now to Professor Luciano Colombo to get the floor for the institutional welcome from the rector of the University of Cagliari.
Thank you, Fabio. So good morning, everyone. On behalf of the rector, Professor Francesco Mola, and my own one, I welcome you at University of Cagliari. It's a great honor and a pleasure to welcome you all at this international workshop on artificial intelligence and academic research. As a vice rector for research of this university, I am really delighted to see this gathering of scholars, all dedicated to exploring the frontiers of artificial intelligence and its deep implications in academic research. As a matter of fact, and according to my current understanding, artificial intelligence stands at the crossroad of scientific progress and society transformation. As such, questioning the convergence of artificial intelligence with quantum computing and cybersecurity is not just an academic curiosity, but indeed a real challenge, shaping the way we will approach complex problems and digital security in an increasingly interconnected world. So in the subtitle of this workshop, we have three keywords: machine learning, quantum computing, and cybersecurity. So machine learning, as one of the most transformative aspects of artificial intelligence, has already made far-reaching changes in quite a few research methodologies across disciplines. Some from predictive modeling in climate science to automated diagnosis in medicine to novel interaction potentials in physics to genomics, to quote just a few examples. The ability of machine learning algorithms to analyze vast data sets and uncover hidden patterns is reshaping the very nature of scientific inquiry. Quantum computing, on the other hand, promises to redefine the boundaries of computational capability, in that by a leverage on superposition and entanglement, quantum algorithms have the potential to master problems that simply fall out of reach of conventional computing. The implications for research are vast, ranging from material science to drug discovery, to even complex optimization tasks underpinning economical and logistic systems. And finally, cybersecurity is an essential pillar of modern digital society. AI-driven security systems are enhancing data protection across many kinds of different industries. As an institution committed to fostering excellence in research, teaching, and technological advancement, our University of Cagliari is proud to host this forward-thinking forum. Our university embraces a multidisciplinary approach and easily recognizes that AI is not confined to a single field, but it rather pervades basically any domain of research. I also like to add that the University of Cagliari is committed to long-term scientific advancements. Quite the opposite than focusing just on next-day applications, we invest in all-around analysis of future emerging horizons, like today AI. Through events like this, we engage our university in foundational research that anticipates technological shifts and ensures sustainable innovation for generations to come. So I extend my gratitude to the speakers and participants who will animate this event. A special thanks to Professor Roberto Giuntini and his collaborators for organizing this meeting, and prompt you to engage actively, exchange ideas, and hopefully, this is something that is really important for me, explore new avenues for future collaborations. So thank you, and I wish you a productive and inspiring workshop. And also enjoy Cagliari.
Thank you, Professor Colombo, for your institutional speech on behalf of the Rector of the University of Cagliari. And now I would like to ask Professor Klaus Mainzer, the President of the European Academy of Sciences and Arts, to get the floor for his speech. Thank you.
Magnificent spectabilis, dear organizers and dear colleagues, as President of the European Academy of Sciences and Arts, it's my pleasure to bring you the greetings of our whole Academy. But at first, let me thank the organizers for this kind invitation to your wonderful country, Italy, always wonderful for Germans, and especially to this beautiful city and its old university. And of course, we will start with a very exciting topic today. And you know, the organizers had their fingers on the pulse of our time with this topic, namely artificial intelligence, the future of artificial intelligence in academic research. And that is, of course, a very exciting topic. And but Europe is no longer in the center. Europe is no longer in the lead, especially with this topic. We all know that. And that was quite different in the past, especially here in Italy, in the time of Renaissance. Modern Europe started here in Italy in the time of Renaissance, and with all these amazing inventors and artists and scientists and philosophers such as Leonardo da Vinci and Galileo Galilei, and the main ideas, the main inventions, the main innovation in the past came up in Europe. And but Europe nowadays is no longer in the center. Our prosperity in Europe is mainly based, and has been mainly based, on the innovation power of the European countries. But in the age of AI, that is no longer the case. You know, the most highly endowed companies nowadays are in AI. And these companies are no longer in Europe, but they are in the US. So the question arises, is that only nowadays AI a topic for big money and big energy? And now the economists tell us that according to their marginal utility theory, if you invest more and more good, for example, money, then in the end the efficiency will decrease in a limit. But there is another encouraging story recently coming up in China. You know, DeepSeek, that was a relatively small startup, but it built a competitor for the ChatGPT, and it became obvious they did not need the very expensive AI chips NVIDIA from the US. They need less energy, they need less money, but they need fresh ideas. Fresh new ideas, for example, concerning the computational architecture of these chatbots. And I think that is amazing because fresh ideas we also have in Europe. For example, here in Italy, a lot of startups and initiatives here in Europe. What is painfully missed in Europe is strategic thinking, is strategic leadership to bring together all these nice initiatives in Europe. So in the end, I think commercialization is fine, but it is not all. It is not sufficient. If you want to have a great long-term breakthrough in research, then it needs, of course, consideration of the foundation. You even need philosophy. Remember quantum computing. Quantum computing started with philosophical thought experiments of Einstein and of Schrödinger. And that is exactly in the spirit of Renaissance. Remember your great hero, Galileo Galilei. He does not only consider himself as a mathematician, but also as a philosopher. And the same is true for Descartes in France, for Newton in the United Kingdom, and for Leibniz in Germany. So in their spirit, I think we should make Europe great again. And that is actually in the spirit of our European Academy of Sciences and Arts. And so let us cooperate together for a new renaissance in Europe. And in that sense, I wish you all the best for your conference, and thank you for your attention.
Thank you, Professor Mainzer, for your inspirational speech. And now it's my pleasure to ask Professor Michael Mols, the director of the Institute for Advanced Study of the Technical University of Munich, to give his speech for us.
So, thank you. Good morning to everybody. At the beginning, I would like to say it was a wonderful talk, Make Europe Great Again, and I will show you a certain contribution of our entrepreneurship university, namely the Technical University of Munich. And I will point on to the Institute for Advanced Study, and I will go into media in res. Next. So the mission and the vision of our Institute for Advanced Study at the Technical University is presented here. It offers opportunities for international scientists to conduct top-level interdisciplinary research exempt from teaching and administrative duties. And I will not go into the further details due to the time. Here I'm showing to you the structure of our university, and I think it's in a certain way comparable with your university here in Cagliari. We have 7 schools, and the schools are given here: TUM School of Computation, Information and Technology, and Roberto Giuntini, when he was working with us, his host was the dean of the school, Hans Bungertz, a mathematician and a specialist in informatics. and they did together philosophy in the sense of Klaus Mainzer, but also in my sense. I think it's very important to bring together engineering, natural sciences with a deeper thinking of philosophy. It was wonderful, pointed out by Klaus. Thank you, Klaus, for that. And now go back. And you see the other schools, they have also fellows, international fellows at the Institute of Advanced Study, here standing in the center of the slide, but cooperating with all those schools of the Technical University of Munich. Maybe I'm mentioning here that myself, I'm a radiation biologist, but also a specialist a clinical specialist in radiation oncology. And it was interesting for me to learn that your university in Cagliari is also, or has also, you call it faculty, we call it schools, a faculty for medicine and health. So again, a certain comparability between our universities. And you see here the number of the fellows, the international fellows, who have their host professors within these different schools of the Technical University of Munich. Next slide, please. A few words with regard to the structure of our institute. You see, we have a wonderful building, the most beautiful residencing during my professional life. Never before I had, even my clinic was as a building, not such wonderful building like this one. We have, of course, a budget. Budget means money coming from the state, Bavaria mainly, but also third-part money, in part coming also from industrial companies. And of course, we have also a team who is running this institute. Then at the Institute, excellent science, I'm mentioning here, we have evaluated the publications of our international fellows cooperating with the hosts, and on the average, in terms of impact factors, the publications are between 1.5, 2 times better than the publications of a normal professor of our university. That means our international guests at our university are contributing by bringing the quality in the different scientific cultures onto a higher level. Besides, also, I should mention, an advantage is also that we have fostered by this construction of our Institute for Advanced Study the interdisciplinary research. We mentioned already bringing together humanities and natural sciences and engineering, but also other sciences. So more than 40 events during the year 2003, and of course sociality between the fellows at this time, about nearly 90 fellows. Then the core of the idea in terms of organization is, as I mentioned, bringing together international scientists with professors from our university, but we are giving them money, not in all the fellowship lines, but in a part of the fellowship lines, we are giving them money also for PhD students or for postdocs, so that they can do together, the international professor with the professor from our university, really high-class research for a time period of 3-4 years. So next slide shows you the different fellowship lines, and I'm only mentioning that I established the philosopher in residence. The money is coming from a German big company, and Roberto Giuntini was the first one as a philosopher in residence at our university. The other fellowship lines I don't mention here. You find that when going onto the homepage of the institute. Next slide shows you that in a couple of years ago, we created the so-called TUM innovation networks. Again, research risking creativity, and a research which is characterized by cross-disciplinary research in cutting-edge topics and building the foundations for future large-scale consortia within the frame of Germany or even within the frame of Europe. So large-scale consortia. The duration of an innovation network is 4 years, and that is also important. The staff equipment is 10 PIs from different schools of our university. Again, the point is interdisciplinarity, plus 10 PhD students. So mainly the money is given for those 10 PhD students. And currently we have running 9 innovation networks. 8 are funded by the Excellence Strategy, that is more or less money coming from the Federal Republic of Germany. And one of the innovation networks is financed by Google company. And the next slide shows you the topics of those innovation networks. You have the names of the innovation networks in the left side column, and I like only to point on the first 3 innovation networks, and you see the first one is devoted to the development of novel materials using machine learning. Second one is diagnosis and treatment of psychological illnesses using artificial intelligence. And the third one is investigation of the nature of life. So that is an innovation network mainly driven by physicists, but also chemists, biologists, etc. So investigation of the nature of life using chemical and biophysical experiments in combination with artificial intelligence and robotics. I'm not presenting the other ones. You can, I think you will provide the talks also to the auditory later on. Okay, next slide shows that at our institute, and that is also in the core of my heart, is also the topic of sustainability located. I think with regard to the future of our societies, global societies, a very important aspect. And when going to the focus groups, a focus group, I mentioned that, means an international professor, a host professor, and mostly a PhD student. So when looking onto those focus groups at our Institute for Advanced Study in 2003, we can, for example, see that 20 of the focus groups can be seen in relation to the 3rd Sustainable Development Goal of the United Nations. The 3rd one, which is good health and well-being. And for example, another is responsible consumption and production, the SDG number 12, 9 focus groups. Next slide, please. And we brought out, also in cooperation with Cloud Minds, during the last years, a couple of books devoted to the topic of sustainability. We did that mainly under the cover of our Senior Excellence Faculty. We both are members of the Senior Excellence Faculty at our university. I'm the speaker of the Senior Excellence Faculty of Technical University of Munich. And here are given the books we brought out during the last years. The newest book, which is coming out during the next weeks, is entitled Novel Nuclear Technologies. Of course, I have not the time to go into details here. but that is especially focusing on fusion energy, but also fission, etc., etc. Next slide. I was able to install a contract a couple of years ago on the basis of my friendship with Michele Nobel, this is Michele Nobel. He was also for a while the leader of the Nobel family in Stockholm, and we made a contract between the Nobel Sustainability Trust and Technical University of Munich, and the contract is foreseeing that the yearly selection based on nomination, selection of sustainability award is led by my institute, by the Institute of Advanced Study at our university. And you see that in 23 we had prize winners, Professor Elena Bu, a Spanish professor, and Professor Lord Nicholas Stern from the School of Economy in London. Last year we had the prize ceremony at the Berkeley University, and the prize winners were professors from Germany, Denmark, and from China. And next slide is showing you that in this year we will have, we are now in the competition based on nominations, as I mentioned already, and the prizes will be given first for leadership implementation, so any sustainability topic. And I would like to ask you if you think that you can contribute to this competition, so please trigger in your international networks nominations. The deadline for the nominations is end of April. The two other topics, more based on research, are smart and sustainable cities, and the third topic is biodiversity. So please, if you feel able, trigger nominations in your international networks. And now I think, that is kind of a summary pointing onto the impact of the Institute for Advanced Study. I would like to mention that now we have nearly 50% of female fellows coming from worldwide, really very renowned universities, America, but also Europe, Italy, etc. And I mentioned already that the work at our institute is done in the sense of being a nucleus for higher caliber research at our university. I mentioned already that in terms of publications, a high quality of the publications of these focus groups. And I mention again that we have this cooperation with the Nobel Sustainability Trust. And with my last slide, I would like to thank you. Thank you.
Thank you indeed, Professor Mols, for your interesting introduction to your institute. And now I ask my friend and distinguished colleague, Professor Riccardo Scateni, the director of the Department of Mathematics and Informatics at the University of Cagliari, to give his speech.
Thank you, Fabio. So I'm a little embarrassed to talk after Professor Mols that showed us so many very nice things. And what I should say about my department, it's kind of 100 of what you showed. We are 75 scientists, and it's Department of Mathematics and Computer Science. Since, University of Cagliari is not so big, so we don't have the possibility to have to separate the department. And talking about, the topic of this event, that is artificial intelligence. I was thinking of what are the relationships between what happened in mathematics, or I'm here at home of the logicians, so forgive me if I'm saying something that is not definitely correct, but I was thinking what happened in the 19th century in philosophy when, I would say Boole and Frege took the logic and brought the logic from only from the field of philosophy and brought it to the field of mathematics, thinking that reasoning formally with the language of mathematics could have helped to explain what the logical framework of reality had explained in the centuries before. And now it seems that we are pretending that bringing the mind, the human mind, from the domain of the neurosciences to the domain of computer science with artificial intelligence would explain everything. I mean, if you are listening to the news every day they are talking about artificial intelligence, and every day, my humble opinion, they're saying so many wrong things about what artificial intelligence is and what can be. I mean, I'm one of the people that was convinced by Roger Penrose that artificial intelligence cannot substitute human mind. So that we can have horizontal applications of artificial intelligence helping us in doing repetitive things, or maybe adding a little bit of creativity, but the creativity of human mind, I don't think that is going to be into the artificial intelligence systems, because I'm convinced, like Penrose was saying, that it's more a quantum mechanical approach, the one that we should use in explaining the human mind. So I think that our role today in the society is also to say that artificial intelligence is not a panacea to all our problems, that we should work steadily to develop applications, but not let everything be in the hands of the big corporation that wants to do only one thing: money. Okay? So I hope that our goal is not only that one, because I mean, money are good for everybody, but I mean, we are not tending to become the next 100 billionaire. Well, maybe. I mean, I'm no longer able to do it, but so I can pretend I don't want to be the next 100 billionaire, okay? So please, let's remind that artificial intelligence was there since, I would say, one century. I mean, since Turing and all the computability theories and so on and so forth, and that we should make our effort for the society, for explaining that it's not only a question of asking to ChatGPT or whatever else tool based on language models, what is the answer to our questions, okay? That these answers are coming from the elaboration of human beings, that these machines are just crunching and repeating, okay? So thank you very much, and excuse me for this.
Thank you, Professor Scateni. And now I ask, my friend and distinguished colleague, Professor Biggio of the Department of Electrical and Electronic Engineering of the University of Cagliari.
Thank you, Fabio. Thank you to all the organizers of this nice conference, and welcome to our international guests. So you're welcome to Cagliari, and it's my pleasure to also welcome you to this nice conference. I think it's going to be a couple of days. We're going to discuss many interesting aspects. I'm here on behalf of the Department of Electronical and Electrical Engineering. even though we are going the elections now. So I used to be the vice director. We're going to elect the new one today, so pardon me if I'm not officially entitled to do this, but it was scheduled beforehand. About the department, we are roughly 100 people, 100 researchers, among professors and tenured teaching assistants, PhD, postdocs, all the roles. So it's pretty big inside the university, I would say. And it was entitled Department of Excellence for the 5 years from 2023 to 2027. This in Italy is a selection across all the universities and departments, and they essentially select the top 180 departments in terms of the evaluation of the research quality. This means not only the types of publications that we have, but also the involvement in projects and all the secondary activities, also the creation of spin-offs and startups on for development of the economy of the territory and so on. I have to say, I've been amazed to see how, all the different areas of science that we cover in the department in the last 5 years have started increasingly using AI over and over. As soon as they manage to understand that the power of data and the knowledge you can extract from there can also improve their applications. So we have now not only the computer engineering group working on AI, but also the control theory and automation group. They use AI to improve the modeling of dynamical systems, for instance. Telecommunications group studying digital twins and so on. So AI is becoming pervasive in our department as well, and as well as in many other areas of science. I have to say we've been kind of pioneering one area of research together with Professor Rowley here, which was about how to hack AI systems into misbehaving or trying to understand their security properties and how you can make them more robust. This was something we really started here in Cagliari, and I think this will be more or less investigated then in the upcoming talks that we'll be giving in this conference. And of course, this is now extremely aligned with all the regulations that are established at the European level. You can think of the AI Act, the Cybersecurity Act, and the many other ones that are upcoming also in other countries. Our research is kindly perfectly aligned and timely with these topics. And of course, we have a lot of involvement in Horizon Europe projects. So we get a lot of funding, not only from the national, the Italian government, but also from the European Union, especially in our department. I think we are quite active. So that's pretty much all I have to say. Again, thanks again, and there'll be chances to speak one-to-one later on.
Thank you, Professor Biggio. And now I ask my friend, great friend, Roberto Giuntini, for the closing speech.
Yeah. On behalf of our head of department, Professor Elisabetta Gola, she's flying to Bangkok now, so good luck, Elisabeth, because it's good luck, really. So this is, I'm going to read her address. Okay. So dear colleagues and guests, I'm very sorry that I cannot extend my greetings in person due to a concurrent conference commitment abroad, Bangkok. So nonetheless, I would have regretted even more not having the opportunity to welcome you at all, and I'm sincerely grateful for kindly agreeing to convey this message on my behalf. This conference represents a highly significant event for the Department of Education, Psychology and Philosophy, as it reflects the scholarly achievements of one of its most prominent research groups. The event brings together a distinguished group of international renowned keynote speakers centered around a theme of great relevance and growing significance within both the scientific and philosophical communities. Speakers with whom the organizers have cultivated a long-standing and fruitful academic dialogue. I would like to express my thanks to Professor Giuntini for conceiving the conference and to the entire research group for their dedicated efforts in organizing. A special thanks goes to Professor Michael Molz, Director of the prestigious Institute for Advanced Study at the Technische Universität München, and to Professor Dr. Klaus Mainzer, President of the esteemed European Academy of Science and Arts, for honoring us with their presence and support. I also extend my sincere appreciation to the department's administrative staff for their invaluable support in the logistical arrangements. It's my hope that your stay in Cagliari will be most enjoyable. I'm confident that this event will provide an important opportunity for scholarly exchange, and I wish you all a most productive and enriching experience. So thank you, Elisabetta.
Okay, so I think we can start the first session of this conference. And the first speaker is Professor Mainzer. He's not here. Okay, so no, he was here, but maybe he's coming. Okay, then just wait a minute. Okay. Okay. So everything is okay? No? Just a minute. So our first speaker is Professor Mainzer, and the title of his talk is The Future of AI in Science and Research, from Foundations to Emerging Technologies. Professor Mainzer, you have 40 minutes, I show 5 minutes, 3 minutes.
Okay. I will try to manage it. Yes, now my contribution as a scientist, the future of AI in science and research, from foundation to emerging technologies. And actually that is on the background of long-term research. These are recent books concerning the foundations of digital and real computing, artificial intelligence and its limits, quantum computing, neuromorphic computing, that means brain-orientated computing, and finally, in the last year, the edition of a handbook of AI. Now, in the following, I will start with remarks on logic and digital computing, and then I will consider the foundations of machine learning, neuromorphic computing, and quantum AI, and then finally, future of hybrid AI technologies. Now, let us start with logic and computing. And here in the beginning, I always like to start with him, with Alan Turing, his famous paper from 36, 37, a theoretical paper on what the concept of digital computing, with his famous Turing machine. And I only want to underline here in that concept the strict separation between processor and memory. And the memory here is illustrated by a tape in the time of Turing, printed with digits, and you know all information can be encoded by digits, and then the processor by this control unit here to manipulate these digits. And technically that was realized for the first time in the 40s by John von Neumann in 1947 with his ENIAC, the first program-controlled digital computer. But actually, historically, Konrad Zuse in Berlin was earlier, namely in 1941 with his Z-drive. But anyway, the point is here I want to make, just from the beginning, digital computing was connected with restricted limits. Limits in the logical foundational sense. Here the famous the famous halting problem of the Turing machine, the undecidability of that problem, and the famous result of the 20th century in the last century by Gödel, namely the first incompleteness theorem of Gödel from 1931, is a consequence of the undecidability of the Turing machine. And in that time, people thought, oh, that is only stuff for philosophers and for perhaps logicians concerning the theoretical limits of digital computing. But then in 1970, Matyashevik, a Russian mathematician, came up with a mathematical exact proof that the halting problem of Turing is mathematically equivalent with a famous problem in mathematics, the 10th problem of Hilbert on Diophantine equation, and that means that this mathematical problem and some others too are in principle not decidable by digital computing. Now, with that in mind, these limits of digital computing, now artificial intelligence. And here in the beginning, there's also Turing with his famous definition from 1950, the Turing test. And you know, the Turing test is a kind of simulation game. That means the system is called intelligent, for example, a Turing machine, if in its reaction and answers it cannot be distinguished from a human by human interrogator communicating with both man and machine, hidden perhaps behind a wall. And in that time, in the beginning of the 50s, people tried to simulate, in the Turing sense, logical thinking, because they thought logic is in the center of human intelligence, and so automated proving in mathematics was started, and later on it was incorporated in the so-called expert systems. That means a logical system in simulating an expert, logical deduction, often a physician, often engineer, and so on. But in the 70s and the 80s, people become aware of the limits of this strictly logical-oriented AI. For example, in robotics. If you try to learn riding a bicycle, that cannot be programmed by logical rules, but it must be trained again and again, and there's some target, and then you did it. And so the idea of machine learning came up in that time. That means we have a computational network here with these symbols in a graph. For example, these nodes represent the neurons and the arrows the synapses, and in the model the synapses are weighted by numbers in order to indicate the neurochemical signals in the human brain. And then it is said, and that is actually one of the rules in modeling the brain, Hebb's rule, that a neuron is said to fire or to be excited if the inputs of the neighbored neurons is larger than a certain threshold value. And then you get a stream of data, a stream of signals, which is led here through the architecture of the neural network, which is divided into layers, such as the neocortex of the human brain. And these data streams are triggered by learning algorithm, training by data, learning. And we can divide certain kinds of learning algorithms. Supervised learning means that the system is at first trained by a certain pattern. For example, a face means a distribution of millions of pixels, and then the system is able to recognize the trained prototype pattern among a huge number of other perceived faces. And reinforcement learning means that the system is able to improve its problem-solving solutions by its own with respect to rewards from the outside. And that is the experience you all have made in ChatGPT, for example, because if you are not satisfied with the answer, then it is trying to give better answers because of your critics, and deep learning only relates to the depth of the system, that means the number of layers. But real-world neural networks nowadays are much more complex than these graphs here. They consist of millions of neurons and millions and billions of synaptic weights, represented mathematically by a network function depending on the input x, that means the sample with which this network is trained, and theta means the distribution of the synaptic weights, and then the system is trained and trained to become better and to approximate a certain target function. And the target function represents the target, for example, the recognition of a certain pattern, or in riding a bicycle to approximate a certain pattern of behavior. Now these complex networks are sometimes criticized today as black boxes because you don't know what is exactly going on in the details here. But from a mathematical point of view, I must say, don't worry, because these kind of mathematics of these complex networks are well known since over 100 years in mathematical physics. In thermodynamics, for example, you consider a liquid which consists of millions or billions of molecules interacting, and the mathematics to describe it is statistical mechanics, which was, for example, introduced by Ludwig Boltzmann and others. So it is well known, and the idea is now to translate this formalism in physics, in thermodynamics, into a cognitive system. And because Boltzmann was the originator of this mathematical approach in physics, it is sometimes called the Boltzmann machine. And the idea is that the molecules, which are interacting with energetic terms here in certain distinguished equilibrium states in this liquid, which can be realized by phase transitions in the physical case, by annealing the system, and then you can get a certain equilibrium states in the liquid in physics. Now to translate it into a cognitive system, that means the neurons are replaced here by the molecules are replaced by neurons, and here are the weights again, no longer energetic interaction, but synaptic weights in the cognitive system. And the energetic states here, these distinguished equilibrium states in the physical system, correspond now to cognitive states, for example, to the targets, which I mentioned before. And so by learning, stochastic learning algorithm, the mathematics is the same like in the Boltzmann approach in statistical physics. They can realize and approximate these targets. And by that, optimization problems can be solved nowadays. Here, such as in the physical example, the energetic landscape is illustrated with these valleys here, and now in the cognitive system, these valleys are interpreted as values of the optimization problem, and of course it is the target to reach in these deepest valleys here the global minimum in order to solve some optimization problem in traffic arrangements, for example, traffic flow optimization. Now, what I wanted to highlight here is a deep connection between physics and AI. And that was the reason that in the last year, the Nobel Prize in Physics was given to AI researchers who started as physicists. For example, Hinton here with this Boltzmann machine, which I illustrated before. Now, my second approach, digital computing, machine learning, and now the second approach, neuromorphic computing. We must not forget that this kind of optimization solutions are realized on classical digital computers. And classical digital computers, you remember the von Neumann architecture, and you remember Turing, they start with the strict separation of memory and processor. And that is illustrated here again. And with that, we will run in the near future into a lot of problems concerning energy consumption. Big energy, not only big money, big energy in the future, because it needs a lot of energy to press the increasing data, nowadays big data, through this von Neumann architecture. And so in the near future, the biggest part of energy consumption of the Earth will be in digitalization, quite different to the human brain. The human brain, you know that perhaps, only need 20 watt for all these amazing abilities. And one of the main reasons is a completely different architecture, namely the network. The network with neurons and with synapses now in the living brain, and here is no strict separation between processor and memory, but in the synapses these functions of processor and memory are integrated. They can both. And there is not only one synapses, there are billions of synapses. So in the living brain, there is no danger of the von Neumann bottleneck. So in machine learning, these networks are still simulated on a digital computer. And so there is no advantage concerning energy consumption. So the question arises, is it possible to realize that in hardware? Yes, we can. A first idea came up in the beginning of the 70s by an electrical engineer from UC Berkeley, Leon Schur, with the so-called memristor. The memristor is, by him predicted theoretically in that time, is a unit, a kind of transistor, which integrates processing and memory. So it can both, such as the living synapse. And so it is a nice candidate to mimic a synapse in the brain. And later on, we wrote some books about that, me more from the mathematical side. And the idea is, at first, you have the living brain. The living brain, the interaction of the living neurons with neurochemical interaction was already modeled by Hodgkin and Huxley. These are the two Nobel Prize winners of medicine from Cambridge, in medicine, by the way. And now the idea is to have a technical model, an electrotechnical model, and the synapses are now replaced or mimicked by the memristors, the memristive networks. And that is not only nice theory, but nowadays it can be built, and I'm in an advisory board of an research cluster, future cluster of the German Ministry of Research. It is called Neurosystems and AI. It is not at the Technical University in Munich, but on the RWTH Aachen in Germany. And here is the architecture of these kind of networks with the memristors, and that is an analog in memory computation bypassing the computational bottleneck, which I mentioned before, with the advantage concerning energy consumption and computational time. Now, in that context, the idea came up, why not considering photonic signals? Not electrical signals, but photonic signals in a photonic-based neuromorphic computer. That would mean an improvement of computation from a millisecond to nanosecond, and an improvement in energy consumption. This is, I will not go in the details, the interconnection in these photonic systems instead of an electronic neuron, now an optoelectronic neuron which generates laser light here, the photons, and they are here led between the optic electronic circuits. Here are the neurons, X and Y, and H means the rates, and they are realized, for example, by a Mach-Sender interferometer. Physically, that is a kind of collection of mirrors in order to reflect the laser light. Now, anyway, I like to call it a brain of light, because you are computing with light here. And in neuromorphic computing, natural neural networks are realized by electronic or photonic circuits, and that would mean a remarkable improvement concerning energy consumption, and that I would also call sustainable AI because of this importance for energy. But there is not only a deep rooting in physics, but also deep rooting in logic and mathematics, especially with neuromorphic computing. And now I come back to the beginning of my talk. You remember Turing, you remember Gödel, and so on. And the main results here are from two famous logicians of the last century. The first, again, Gödel. There exist definable but undecidable sets over the digits. That is the Turing problem of halting problem, undecidability. That means the theoretical expression for the limits of digital computing. But 20 years later, another famous logician came up, Alfred Tarski, and he proved every definable set over the real numbers is decidable over real numbers, and that means analog computing with real numbers, neuromorphic computing, may overcome the limits of digital computing. For example, Hilbert-Sten's problem. It is now decidable over the real numbers. But not only these theoretical results in mathematics. Recently, also discussion of real-world problems in medicine, namely the so-called inverse problem of medical imaging. The situation is the following. You have an object in medicine, a tissue, and that is mapped, that is measured. That means by MRI or CT, and that means mathematically here is the object X, and then it is mapped on a noisy measurement. The measurement is always noisy. This is a mathematical expression here, and the question is it possible from this noisy measurement to reconstruct the original object by digital computing? And mathematically, that means it is a task of minimization, because you have to minimize the noise of the measurement. Is that possible by digital computing? And solving it nowadays with AI means machine learning. And machine learning means you apply neural network. And neural network application means you have to train the network. So the question is it possible to train a network by the samples of the difference between the pairs of the object X and the measurement Y? You are training that with these samples in order to diminish the difference. Is that possible by a digital computer? And the hard result in mathematics, not in physics, in mathematics, is digital approximability with arbitrary accuracy is in principle not possible. There is a lower bound of algorithmic accuracy with digital network. In the background is Gödel and Turing. But now, in the background with Tarski, analog algorithms on neuromorphic computers could solve the approximation with arbitrary accuracy. So neuromorphic computing would not only mean an advantage in sustainable energy consumption, but also in computational accuracy. And now my last approach, of course, here, quantum computing. And here it is well known. In the center is here the superposition and the quantum bit. And the hardware in this context can, for example, be realized by photons. Again, our photons. 0 and 1, the bits can be represented by here vertically and horizontally polarized photons, but in the superposition you also consider the intermediate state between 0 and 1 with more or less probability to be 0 and 1, and that is the quantum bit here realized on a photon. But here on the list on the left you can see there are a lot of other technical realization nowadays in quantum computing. I will come back to that later on. Now, the great advantages, of course, in classical computing, for example, the von Neumann architecture, you have to process and to memory step by step after each step in this kind of von Neumann architecture, but in quantum parallelism, all possible input bits are switched into the superposition of 0 and 1 with an enormous acceleration of computation. Perhaps you all know that, the Shor algorithm to solve the factorization problem, which cannot be handled by classical computers. But as far as we know, because this is a main difference to neuromorphic computing. In neuromorphic computing, you remember, you can prove mathematically in principle that a digital solution is not possible. Here, it is not excluded that someone will come up here in the audience and will present a classical digital solution of that problem. Now, anyway, the deep connection of machine learning with physics. I mentioned the Boltzmann machine, and here some time earlier, John Hopfield, also a physicist, solid-state physicist, came up with the Hopfield system. And he also, in the beginning, considered a complex physical system, for example, a magnet here, with different atomic dipoles up and down. At first, the distribution of the state is irregular, and then by phase transition, that means by annealing, we can arrange that all these dipoles are jumping mainly into one direction. That means a regular pattern emerges and the whole system is magnetized. And then it is translated into computing, cognitive AI with the Hopfield system. Instead of the neurons, now black and white neurons, and instead of the phase transition, a learning algorithm to recognize the regular pattern which was previously changed. Also Hopfield, the Nobel Prize in physics in the last year. And now the application to quantum mechanics, quantum computing, in order to illustrate the connection. We have to replace in the Hopfield system these alternative states, black and white or 0 and 1 of the units by the quantum bits, and they are sometimes illustrated here by the so-called Bloch spheres. And here it is a nice illustration, the Bloch sphere. A pointer is running between these extreme values at the poles of the sphere 0 and 1, indicating the probability to be more or less 0. And then with that, in the checkerboard here of the Hopfield system, black and white, not only, but also these immediate states here illustrated, and the Bloch sphere here, the superposition with equal probability of 0 and 1, perhaps illustrated by the color gray. Technically, it could be interpreted as a defective pixel besides the black and white pixel. And then by translation of the Hopfield learning algorithm into to quantum formalism, you can also realize a quantum Hopfield system. And that can be generalized to multi-layered neural networks. You remember what I mentioned before. That means, again, that now in the Boltzmann machine, you have to replace the neurons by quantum neurons, quantum bits. That means the bits of the energy function are replaced by qubits. The number of the variables correspond to n to n, 2 to n possible states, and instead of the n-dimensional vectors in the classical Boltzmann machine, you consider now the 2 to n dimensional operators and the classical energy function by the Hamiltonian operator, and so on and so on. So again, you can consider optimization problems. I mentioned that before. Now with the advantage of quantum computing with the superposition, but there is another nice effect in quantum mechanics, the tunneling effect here. And that means, according to Heisenberg's uncertainty principle, there is not only a probability that a particle is before a barrier of energy, but also behind it. And that is the basis for saying, or interpreted is, the particle is penetrating the energy barrier. That means it is not necessary, such as in the classical Boltzmann machine, to overcome this mountain of energy, and that means in the end, of course, also shortening the time. But besides superposition and tunneling, there is, of course, the other great principle in quantum mechanics, and that is entanglement. Entanglement is a great philosophy. I mentioned that in my institutional speech. But the point is the great insight of Einstein, that in the quantum physical world it must be possible that distant locations can be entangled in a quantum state, and you know that was confirmed in physics in the beginning of the 80s, and nowadays it is a basis of quantum communication. That is illustrated here technologically by the satellite technology. These are the distant locations for communication, and they are entangled by photon rays which are entangled, and that has, of course, a great advantage for cybersecurity, because any attack in this entangled system could be observed anywhere in this entangled system immediately. Now, my last remark concerning quantum communication is very recently. In the beginning, in that part, I mentioned that all these different quantum computing approaches are realized with different technical equipments. I only highlighted the photonic approach, and that is, of course, a problem, because in digital computing, you know, the user, we all must not have any idea of electrotechnology, but we can use it on the software, hardware independent level. And recently, a quantum network operating system came up to realize that. That is illustrated here. There are the different equipments in quantum mechanics. They can be connected by entanglement, but on the user level, there is an independent and hardware independent software. And I highlighted that in the end of my quantum computing part, because coming now to my last remarks concerning the future of hybrid technology. Actually, we can observe, that was the topic of this talk, two main strategic developments in technology. First is digital computing, here in the red arrow. And that means, following Moore's law, we will run into limitations and miniaturizations with nano and atomic scaling that is illustrated here, and the traditional semiconductor technology must be overcome by quantum computing. I mentioned that. But the other tendency is sometimes called more than Moore technology, and that means this kind of analog computing, especially with sensors in robotics, real computing. And with this kind of neuromorphic computing here in blue, and the target is, of course, to integrate both approaches, and that has a very, very practical vision for the supercomputing center of the future. In the computing center of the future, that is my vision and my interpretation. All these different approaches will be integrated. That means machine learning with digital computing, neuromorphic computing, quantum computing, because all these different approaches have several advantages, but also several limitations. I highlighted that. And now for the user, that means in this future of a supercomputing center, that must be hardware independent for using the problems. It is nowadays only mainly known in digital computing, but that will also be the goal here in the other approaches. And that would mean, of course, cybersecurity, an improvement in cybersecurity. I mentioned that especially for quantum communication. And so in the end, coming back to Europe, we need international AI standardization, especially here in Europe between the different countries, and I think a certification for sustainable and responsible innovation for Europe. I thank you for your attention.
Thank you for your beautiful talk. And so now we have about 5-10 minutes for questions. Okay, please come here. Yeah.
Thank you for your inspiring talk. I think I saw many of the nice ingredients to be combined together. I was wondering if so I've been reading a bit about photonics and the neuromorphic architecture you described. I know that they have very small latency, so you can do the computation much faster, but it's also very difficult to control light at the current state of the art, as far as I know. So do you have insights on the scalability of these techniques? So now I know that they have devices with few parameters, but compared to the large AI system with billions of parameters, how can we somehow match this gap?
Yeah, one must say the established neuromorphic approach is the memoristic one. And I can observe that in the research cluster, which I mentioned. And one must say the photonic approach is in its infancy. And, but I can observe that in this research cluster that there is a kind of competition. We have, so to say, in the research cluster, two approaches as a kind of competition, and in the forehead is memoristic, but I think photonic has a lot of advantages. We can observe that also at the Technical University of Munich. You know, in quantum computing, we have these approaches which needs these very highly sophisticated technical equipment to cool down the whole system. But then in its infancy there are also photonic approaches in order to bypass these problems. And personally, I think that will be the future. I cannot imagine that we need for quantum computing these deep temperature equipment. It's unbelievable. You see such a machinery interdisciplinary, and you say, wow, that's a quantum. No, that's not a quantum computer, is that. But that is only equipment to arrange that. That's nice for the lab. And I think the situation here is similar in neuromorphic computing. And of course, that will need some time. And there are a lot of very, very difficult and tricky problems. You mentioned that. But in the end, personally, I think that will be at least a long-term future. Yeah, but that is the situation now in research.
Yes, please. Yeah, come here. No, it's impossible. I'm sorry. Should come here.
Thank you, Klaus. As a physician, I would like, or you touched also the medical field, and for me, your talks are sometimes too much abstract, if I can say so, because as a physician, it's difficult for me to understand the deepness of mathematics and the physics. But however, I understood that you have, when considering medicine, you have compared neuromorphic computing with quantum computing. Is that correct, what I'm saying? Yeah, so please, could you give one example, one very concrete example, when going into the field of medicine, which question, very concrete question in medicine, you would give an answer either by one or the other, or a hybrid method?
Now, that was an example which recently came up. You are right, that is always my claim, to connect deep physical, deep logical, mathematical foundation with the applications, because that is sometimes forgotten today. The people, we mentioned that in our opening talks, they are only oriented to money, big energy. No, the long-term breakthroughs were made possible by long-term considering this connection with the foundation. That's my opening remark here. And now coming to medicine. The main point here was, by neuromorphic computing, that in digital computing, I mentioned that in the beginning, and many applied computer scientists are not aware of that. I think so. That this digital computing is just from the beginning, from the time of Turing, connected with limits of computing, the undecidable problem of the halting problem. And people thought, oh, that's abstract. That is only for logicians and for philosophers. No, the next step was even in mathematics. There are problems in mathematics which in principle are not decidable, but the main point is with a digital computer. It is not said that it is, in a philosophical sense, undecidability. If you extend the approach to real computing, now mathematically speaking, you are computing with the real numbers, then the problems that can be solved, Tarski is now in the background, it can be solved by this kind of real computing. The problem is real computing technically realizable? And now neuromorphic computing came in. A neuromorphic computer is in some sense an analog computer with these real states. And there is a lot of research done recently, but mainly in the context of foundational research. For example, in Munich, Michael, we have a research group, the AI center there, together with the LMU and the technical university, and they are discussing exactly this point. But that is deep foundational research, a lot of tricky mathematics, I must say. But now my medical example. This medical example may be for you as a practical physician very simple. There is a tissue, and you know there are MRI and CT imaging of the real object. And mathematically expressed, the real object is X and Y is the measurement. And the measurement here is mathematically represented by this term, and here there is E, that means noisy. It represents in the mathematical coin, measurement is always noisy, as we know. So the problem here is the following. Is it possible to reconstruct from this noisy measurement the original object? That is called reconstruction. That's a reconstruction problem. Is that possible? And by digital computer, by every world computer. Now the result is, in the background, these foundational results. The idea is to solve the problem by machine learning. And machine learning means you apply a neural network. And applying a neural network means you have to train the neural network to better and better approach the original target, namely here this reconstruction mapping. And then this kind of neural network is trained. That means actually there are samples of pairs of the original objects X and the measurement Y, and with a finite sample it is trained, the system, in order to diminish the difference, that means minimization, the difference between X and Y. That is the idea. And so we would say, oh, why not? And now Gödel comes in, now Turing comes in, because you can prove mathematically, and that is a very tricky proof. It is an indirect proof, but that doesn't matter here. Anyway, you can prove exactly that is not possible, because if you try to make this approximation of the neural network to the reconstruction mapping more and more precise, then you can prove there is actually a lower bound of algorithmical accuracy. And that has importance for the practical physicians. Of course, you can have approximation on the digital computer, but you can mathematically prove, and in medicine, the people become more and more ambitious and want to have better and better results. You can prove mathematically that is only possible to some degree. It is in principle not possible to improve the accuracy in an arbitrary way. But it would be possible if you use a neuromorphic computer, this kind of analog computer, and there is in the background only a very fundamental result in mathematics, namely Tarski, who proved that these kind of problems are solvable. So that is the practical point. It's only one example, you know. Yeah?
I make a very, very short
Yeah?
comment. Coming from my experience in my field of radiation oncology, I'm cooperating with physicists. In every department of radiation oncology, you have physicists. And I learned from the cooperation that in many, many cases, we are running into a kind of an over-accuracy. Let me say too much mathematics, which is not needed. And therefore, I would recommend to bring that into a context of really very, very practical questions.
Yeah, that would be the next step, but my point here was to illustrate that even the practical applications in medicine and elsewhere, not only mathematics, that is my point, the applied science nowadays, which seems to be only oriented to practical problem solving and to money and things like that. A long-term breakthrough needs a combination with this kind of fundamental research, because quantum computing would not be possible if in the beginning there would not be such a guy as Einstein, which was a philosophical inspired great scientist, which is philosophical question, what is reality? It's an old philosophical question. And then trying to solve that leads to these amazing quantum technologies, very practical nowadays, with which you can also earn a lot of money.
We thank Professor Mainzer. And so we are going on with the next speaker. Our next speaker is Professor Sergioli from the University of Cagliari. And his talk is, the title is Quantum Information and Machine Learning, a Marriage of Love or Convenience.
Okay. Hello everybody, thank you very much. I'm very happy to be here and to join with all of you these 3 days where we will look for some bridge that can connect different topics, different aspects of nowadays research that is mostly related to quantum information, quantum computation, foundations of science, but also machine learning, cybersecurity, with the aim, with the purpose to find fresh idea, just to keep some expression that was used by Professor Mainzer in this talk today. I like it so much, this word, fresh idea. So, this talk, the title is Quantum Information Meets Machine Learning, a Marriage of Love or Convenience. So I decided for this romantic title because I also like to convince you that the answer is both, okay? My purpose in the next minutes will be to convince you that the correct answer for this question is both. And okay, I am just a speaker because the author of this result are not only me, but also Professor Giuntini and two very brilliant PhD students of us that are Andrés Granda Arango, that is here or everywhere else, and Carlo Cuccu that is there. Okay, so generally I like to introduce this topic by introducing my daughter a few months ago, and she in this picture has a pink T-shirt, and I like to make you a kind of provocative question. So, can you find in your mobile a picture when some relative of yours had a pink T-shirt? I think that you can. I think that you can. If you scroll, you will be able to do this. The point is that very probably you need time. You need time. Why you need time? Because now we don't have more a problem in our device. We can storage all the memory we need. Basically, the average number of pictures that we keep in our mobile is 1,000 now, not 100, but 1,000. And so, if we want to pick just the information we need, we need more time. We need more time to retrieve the information we need, because now the problem nowadays changed. It's no more storage information. We have basically no limits also using the cloud. We have no limits of the information that we can store. So the data we can store. But data is not the same of information, because big data means potentially a huge amount of information. But the time that we need to retrieve this information generally is longer. Indeed, now we are in the age of big data, and so the extraction of information is getting a real problem. So, what is big data? Big data means big data, really big data, because, well, the first definition I found, but I don't know if it is really the first, is in about 10 years ago, and maybe more, where like a big data or very large data was considered something like 10 to 12 number of bits. So it's a quite huge amount of data. But of course, this definition
is increasing and increasing and increasing by the time. If we consider that this definition was provided more than 10 years ago, now we can consider like a big data something that is biggest and biggest with respect to this, let's say, first definition. So, in other words, let me summarize this first, let's say, 5 minutes talk. In other words, enlarging the dimension of data provides a good thing because it increases the potential information, good, but at the same time makes the extraction of the required information harder, and it is not good, Okay, so everyone here knows quantum computation, knows the history of quantum computation, and we know that by considering some important property of quantum theory, such as entanglement, superposition, parallel evaluation, and so on, it's possible to speed up, it's possible to provide a speed up of some algorithm, okay? In principle, it's possible to do it. Well, on the other hand, by following the Moore's law, we know that we are going in a continuous miniaturization of the hardware component of a computer. So in a certain sense, the common usage of quantum computer is not the future. Don't say the future of quantum computer because it is what actually really happened. And it is, for instance, just to say that it is not so futuristic, I refer to one of the quantum computers that we have in Europe. I refer to the Leibniz Rechenzentrum, but I don't want to anticipate something that will be described in more and more detail today. Okay, in any case, we know, but already in the 2020, was declared the first time what is called the quantum supremacy. Because, well, we know that a quantum computer can speed up the computation, but how much is this speed up? How much? Really a speed up, because the new quantum computer, this is what declared in the 2020, and that was remarked again in the years after. The new quantum computer can perform a calculation in 20 seconds that will take more than 500 million years. So the supremacy is really, 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 really huge. So, and at the moment, this is just, I don't know that you cannot read, but it's not important because what is interesting is just to see that it is a Wikipedia page where we know that a number of quantum processors that actually are used in Europe or maybe in the world, I don't remember, maybe in the world, yes, sorry. And that are already many. So we are a number of quantum processors with different technologies and so on that we can actually use around the world. So summarizing, the main problem of machine learning with big data is the time complexity we need to retrieve the information we want. But on the other hand, the quantum computation provides the advantage to speed up the computation. So I already can provide an answer to the question, which kind of marriage is. It's not a convenience marriage, it's a kind of unavoidable marriage, because one requires the other, okay? So in a certain sense, we are very happy to have this connection. I say this because, well, we are in a period where very, very often we listen about quantum-inspired something or a quantum application in something. Okay, sometimes there is, let's say, well, a lot of too much in this, because sometimes for any kind of phenomena where there are some properties that are that come into a kind of holistic matter, sometimes say, oh, it's something holistic, it's a quantum behavior. Well, it's not a quantum behavior, it's just holistic. But that we have not quantum every time we are something holistic, okay? Quantum is something more. Quantum is quantum. That involves also holistic, of course, but it's something more. And in this case, quantum computation and machine learning is not an abuse, is a kind of a really, really unavoidable connection. But I like now to make you a foundational question. And can quantum information theory help classical machine learning even by using at the first stage classical computer only? So this is a question that I would like to provide you a positive answer in the after minutes. Okay, and again, what is this inspiration? Why we speak about inspiration? Well, this inspiration is not reduced at a level of analogy. Again, I like to stress this. But what we will show is that this inspiration will provide a real benefit in machine learning, and this real benefit will be not only related to the speed up of the computation, but even to the increasing of the accuracy of the process. So we will show, and maybe it is something quite new also for the community that is working on quantum machine learning, that in principle, quantum theory is not useful only to provide speed up, but is useful only to increase accuracy. So this is the point of the after few minutes. Okay, we will focus on a particular problem in machine learning. It is the classification problem that I will very, very briefly describe. I don't like in this talk to come in too many details, okay? I have in the slide details, but I like just to provide a qualitative description, and of course, in case of questions, please, I like so much to be interrupted during the talk. So if you need, please don't hesitate to stop me. Okay, we know we know very well what is the paradigm of the supervised machine learning, the supervised scenario. So we have a data set divided in a training and test set, and the training set is divided in different classes. So I will provide a classification among, for instance, different kind of animals, like cats, dogs, rabbits, and so on. First, I divide the data set in training and test data set. In the test data set, the animals are mixed all together. On the other hand, in the training data set, so the set is divided in different classes. This part of the data set will be used to train the classifier, and this part of the data set will be used to understand whether the classifier works in an effective or not way. Okay, so this is a kind of a supervised scenario. It means that all the objects that are involved here, even of the both of the training and the test set, are already labeled. So we already know whether they are cats or dogs. And our aim is not to classify in the first instance, but just to measure the performance of the classifier. Okay, and we know that we have different kind of classifier with different accuracy, with different mathematics, and with different methods. So what we want to do is to take inspiration from quantum information to provide an effective quantum-inspired classifier. Okay, so we need to fill 3 different steps. The first is the encoding, because we deal with classical objects. Okay, we deal with animals, we deal with students, we deal with different diseases, we deal with different things. We have to classify, and after we have to decode and come again in the initial data set. Okay, first of all, what is the encoding? Of course, we cannot transform a rabbit in a photon. Of course not, because our encoding is just a matter of mathematical things. Okay, and so, okay, I don't come into detail again, but first of all, okay, the encoding, we have different way to encode objects. what is important to know, without again coming to detail, is that what we encode is a vector that is a vector of features that characterize the object we are dealing with. For instance, a rabbit. A rabbit, we decide to consider the weight of the rabbit, the length of the tail, and something more. So we have a vector. And we encode in some mathematical way this vector into an object that is a density operator, that is the standard object used to describe physical quantities, physical systems. So we are just comparing two different descriptions. The real description of a rabbit and the description of a quantum object, a quantum particle, a system of quantum particles, and so on. There are many different ways to do this with different geometrical approach. Okay? Okay. So, after this, there is something very important that we like to understand. Okay, that is, we are coming into a different geometrical topology. It is very, very important, also from a foundational point of view. Because if we consider, for the sake of simplicity, a vector of two features that can be plotted in a very simple way in a plan, okay, in a plan. After this encoding, and if you consider, for instance, this object like two data sets, the blue dots and the green dots, okay? Okay, how can you distinguish the set of the blue dots and the set of the green dots? You can do that, there is one strategy, it's not the only, by considering the centroid of the two classes. If you look, for instance, at the, this data set, okay, you can see you have the red data set and the blue data set. If you consider the centroid of the blue and the centroid of the red, and you consider the axis, the line between these two centroids, this line is just the classifier. So all the point that is upper this line will be classified as blue, all the point that are below is classified as red. Of course, this classifier can make mistake, and it is correspond to the accuracy of the classifier. We try to do this, we try to do the same, but for instance, you can see that for this kind of data set, this problem is more tricky, because in this case, both the two classes, the blue one and the green one, has the same centroid. In this case, if you only consider the centroid, it's very difficult to distinguish between the blue class and the green class. It's basically impossible because they are the same centroid. On the other hand, if you consider this translation, if you consider instead of a classical centroid, the quantum centroid that is given by this very simple formula. So, first of all, we translate each object of the data set in terms of quantum object. Second step, we calculate the centroid, but no more centroid of a real point, but centroid of density matrices. And we obtain another density matrices, so another physical state, but this physical state does not correspond to the quantum translation of the classical centroid. It's a new point, it's a new physical state that has not a correspondent in the real world. It's something that is completely only quantum. So starting from real, encoding from real to quantum, and provide a centroid, we now are in a new world. We now are in a completely quantum world, and we already can see a first glance of advantage. A first glance of advantage is given by the fact that if you consider classical centroid, you cannot distinguish between these two classes. But the quantum centroid of these two classes are different. So even if the classical centroid are the same, the quantum centroid are different. So, in principle, allows us to provide a better distinguishment between the two classes. But this is only the first kind of advantage. Okay. What we refer to is, again, something that is typical of quantum mechanics, and that has not any kind of quantum analogs in classical setting. That is a quantum state discrimination that, again, I describe in a very, very bit without coming into detail. Let us consider that two friends, like Alice and Bob, I'm not original in considering this name, but that's fine, Alice and Bob, agree to share some physical states, let's say rho 1, rho 2, rho m. And at a certain moment, Alice sent one of these states to Bob, okay, and Bob received this state. So Bob has to recognize which one is the state that he are receiving from Alice. As you can understand, from a classical point of view, this problem has not meaning. If I decide with you to share a set with a green ball, a blue ball, a red ball, okay, and you send me the red ball, I look at the red ball and say, okay, it's a red ball, no problem at all. But as you know, in a quantum framework, everything changes, because if I look the red ball in a quantum scenario, I am interacting with the red ball. I am changing the red ball. The red ball is no more the red ball, it's something different. So, in the quantum scenario, the question is, which one is the measure, the best, the optimal measure that Bob can use in order to have the better chance to pick exactly what is the correct state that was sent from Alice. So it's more tricky, because now the challenge is just to follow what is the measurement. The measurement means also the apparatus, the physical apparatus that Bob has to use in order to know with a better probability as possible which one is the state that was sent from Alice. So it's very, very more tricky. And so the question is, find the apparatus, find the measurement. What is the measure, the optimal measurement to do this? Okay, and I don't like to come into detail, but in the case of binary, in the case of binary discrimination, so in the case where they in principle agree over only two possible states, Hellstrom in the 1976 provide an optimal measurement. The protocol is not hard, but I don't like to describe in detail it. What is important is that by using this protocol, Hellstrom found two operators, P plus and P minus. These operators, P plus and P minus, form the measure that is optimal in order to maximize the probability. So he found just two mathematical operators that are able to maximize the probability that I defined here. And this maximal probability is called just Hellstrom bound. So the probability is not 1, of course, because if the two states are not orthogonal, never we can be completely sure about which one is the state that was sent. Not sure, but we can maximize the probability. And the probability is this one, the maximal probability, that is given only if we use this measurement given by P plus and P minus. Intuitively, P plus and P minus represent the property for the system to be correctly identified as being in the state rho 1 or in the state rho 2. Okay? And in a certain sense, the Hellstrom bound can be seen as a measurement of distinguishability between these two states. Okay, so till now, I was speaking before about machine learning, classification, and centroid. After, I was speaking about quantum state discrimination. What is the connection? Well, the connection is given by the fact that if these two states that I want to discriminate are just the centroid of two classes after a given encoding, I can very easily define this quantum-inspired classifier. Basically, if I pick a point from a test data set, I encode this point, and this point becomes a density operator, and I calculate, by following a standard Born rule, the probability by using P plus and P minus that this rho X is closer, let's say, is closer to the class of the cats or to the class of the dog, I am in this way able to classify a classical object by appealing to quantum state discrimination theory. Quantum state discrimination theory. So, this is the idea, and basically the physical motivation is summarized by this motto, let's say, that better is the discrimination between two quantum centroids, and better is, and more performant is the classifier. But basically, it is how generally classifiers works. Because if we are able to distinguish two centroids, we are in a very good way able to distinguish between between two classes. And okay, after this idea, we want to know a thing that is not, let's say, quite important, if this idea works or not. And in order to see this, we applied this quantum-inspired classifier to different data sets, 11 different data sets, 14 different data sets compared with different standard classifier. We published this result a few years ago in PLOS ONE, and what we realized was that by increasing the Elstrom bound, so by increasing the degree of distinguishability between the two quantum centroids, we really have an increasing of the balanced accuracy. So this is completely in agreement with what we supposed. So it was completely in agreement that greater is the Elstrom bound, i.e. the measure of distinguishability, and greater will be the accuracy of the system, of the classifier. Okay, so, and, okay, we made some experiment, and we compared this classifier with other standard classifiers, and what we see is that generally, okay, I have not the final rank, okay, compared with other standard classifier, our classifier generally outperforms the other. And it is we think, let's say, promising result, okay? And so this is just summarizing what we said till now. We have a different data set, classical data set. We encode this in quantum object. We have quantum centroid, and a good discrimination between quantum centroid means a high level of Elstrom bound. On the other hand, it means a good classification or high level of the accuracy. That's not all, because we can again exploit quantum foundations, let's say, or quantum information, to provide a further benefit. And this is given by the fact that, unlike the classical scenario, in the quantum one, if we provide, let's say, copies of a given status, of a given state, we provide additional information. It is not intuitive in a classical framework, but it is well known in a quantum one. So, if we, instead of using the state rho that comes from an encoding, we put in place of the state rho a tensor product of rho time and time for itself, we provide an additional information. This additional information is, again, proved also experimentally. Indeed, we can see that by providing copies of each element of the dataset, we again have an increasing of the accuracy. And okay, we have also, and what we see at the end is that our quantum inspired classifier with copies, with this number 4, 3, 2, 1 means the number of copies, on the average overcomes all the other standard classifier. All the other standard classifier. Okay, again, used over 14 data set and compared with 11 different classifiers. Okay, so I prefer to move on the practical application, and we apply this method also in different bioimaging purpose, with result that, again, I don't want to say that are groundbreaking, but at least very promising. I like to do this. Okay, we provide in the context of idiopathic pulmonary fibrosis for a kind of a preliminary experiment, but mostly in a large side experiment in the context of clonogenic assay evaluation. And we did it in collaboration with the University of Cambridge and the Biomedical Imaging Institute of the CNR in Catania, in Sicily. Okay, so what is, a clonogenic assay is a quantification technique of the survival degree of in vitro cell cultures, which is based on the ability of a single cell to grow and form a colony of cells after a given treatment. Sorry if I speak in a very trivial way about this, but it's just the idea I had of this. And the question is, after a given treatment, how many cell colonies can be individuated? So, this is the pictures, this is the kind of pictures we was dealing with, where, this is, as you can see, this is considered as a colony of cells, And the question, the purpose is just to counter the number of colonies, because it's very, very effective in order to prevent some disease or make also some diagnosis. It's very important. It's very important. Recent results show how, by a classification between pixel X belongs to the colony or pixel X belongs to the background, it is possible to have information about the number of the colonies. So, if we provide a good classification pixel by pixel for each point of this picture, we can also have a good information about the number of the colony of a given picture. Okay, so the setup of the experiment was not a very trivial stage, because the communication between us and the people who was working biomedicine was not easy at the first glance, because we needed to decide for a common technology. Because when I say, give me a vector of features, they say, what do you mean? I can understand in a plenty of different ways what you are asking me. And so that was the setup was a very interesting part of the collaboration, and also I like to say very, very, very insightful for all of us, because allows all of us to understand important things regarding the other side, and was very, 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 very long but nice. Long but, of course, not useless. Very, 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 very useful. So, in total, we have considered 4 cell lines, and each line is given by 30 different pictures. Each pictures were given by, thousands of pixels, and in total, we'll deal with more than 10 millions of data. So, really a large data set. And each pixel was featured not only based on the position, okay? Not only this, but also regarding other features, other medical, okay, biomedical features. Okay, we compared the performance of our classifier, again, with respect of other well-performing classifier, and what we understand at the end, what we obtained at the end, was a very nice result for us. That our classifier, that is the HQC, was ranked in the, okay, we applied in the 4 different cases, for 4 different parts of the big picture that we analyzed. And what we will realize is that in 3 over 4 of these, our classifier again was ranked in the first 3 among the 15 classifiers we compared. So again, we thought that our classifier, we don't say it's already ready, but is very promising also for an application in biomedicine. Okay, there are many things that I can say, but I like to conclude by saying an important things. I said at the beginning that a very nice point is that everything I showed you does not involve quantum computers, because it's only obtained by referring to classical computer, by referring to quantum information using classical computer. And the aim is just to provide a good accuracy, an increasing of accuracy. But in principle, and not only in principle, it's also possible to implement at least the test part of this in a quantum computer, because there is a well-known Newmark theorem that allows. Indeed, what we provided was a simulation of the test part of this classifier in a quantum computer, in the IBM quantum computer. And again, the results was really close to the expected one. It means something that for us is very promising, very important, and that is the end of the talk. That is, in principle, by appealing to quantum information, but by using also quantum computation, we can put together 2 benefits. First, increase the accuracy, but the second, increase also the speed up of the computation. So not only speed up, but also accuracy, both together. And this is the end. But, okay, of course, walk us to the point. Thank you.
Thank you, Giuseppe, for your talk. So we have 5, maybe few more minutes for questions. Yes? Oh, okay.
What are the limitations for running this application on quantum computers? Is the depth of the circuit, number of qubits, or anything else?
Yeah. Thank you, Luigi. Yes, there are strong limitations. Basically, what I show you here by this circuit is a very toy model, because it's given by a short data set, given only 2 features and 2 classes. And as you can see, the circuit is already not too long, but long enough. But the most important point is that this circuit is able to represent only the test part, not the training. The training is the most consuming part of the algorithm, and actually we don't have the quantum algorithm that is able to provide the training part of our quantum-inspired classifier. This is a challenging. I invite all of you to collaborate with us in order to find, let's say, an optimal circuit that could be able to provide not only in the test, but also the training part. We can also consider that, as can happen very often, at this moment we can consider also emerging between classical and quantum computation and have some kind of hybrid result. At the moment we can also be satisfied with this. But at the moment, it's a good question. It's, well, the application has some limitation. Yeah. Between two classes. And, okay, after this idea, we want to know and think that is not, let's say, quite important if this idea works or not. And in order to see this, we applied this quantum inspired classifier to different data sets. 11 different data sets. 14 different data sets compared with different standard classifier. We published between two classes. And okay, after this idea, we want to know and think that is not, let's say, quite important if this idea works or not. And in order to see this, we applied this quantum inspired classifier to different data sets. 11 different data sets. 14 different data sets compared with different standard classifier. We published this result a few years ago in PLOS ONE. And what we realized was that by increasing the Elstrom bound, so by increasing the degree of distinguishability between the two quantum centroids, we really have an increasing of the balanced accuracy. So this is completely in agreement with what we supposed. So it was completely in agreement between two classes. And okay, after this idea, we want to know and think that is not, let's say, quite important if this idea works or not. And in order to see this, we applied this quantum inspired classifier to different data sets. 11 different data sets. 14 different data sets compared with different standard classifier. We published this result a few years ago in PLOS ONE. And what we realized was that by increasing the Elstrom bound, so by increasing the degree of distinguishability between the two quantum centroids, we really have an increasing of the balanced accuracy. So this is completely in agreement with what we supposed. So it was completely in agreement that greater is the Elstrom bound, i.e. the measure of distinguishability, and greater will be the accuracy of the system, of the classifier. Okay, so, and, okay, we made some experiment, and we compared this classifier with other standard classifiers, and what we see is that generally, okay, I have not the final rank, okay, compared with other standard classifier, our classifier generally outperforms the other. And we think, let's say, promising result, okay? And so this is just summarizing what we said till now. We have different data set, classical data sets. We encode this in between two classes. And okay, after this idea, we want to know and think that is not, let's say, quite important if this idea works or not. And in order to see this, we applied this quantum inspired classifier to different data sets. 11 different data sets. 14 different data sets compared with different standard classifier. We published this result a few years ago in PLOS ONE, and what we realized was that by increasing the Elstrom bound, so by increasing the degree of distinguishability between the two quantum centroids, we really have an increasing of the balanced accuracy. So this is completely in agreement with what we supposed. So it was completely in agreement that greater is the Elstrom bound, i.e. the measure of distinguishability, and greater will be the accuracy of the system, of the classifier. Okay, so, and, okay, we made some experiment, and we compared this classifier with other standard classifiers, and what we see is that generally, okay, I have not the final rank, okay, compared with other standard classifier, our classifier generally outperforms the other. And it is we think, let's say, promising result, okay? And so this is just summarizing what we said till now. We have a different data set, classical data set. We encode this in quantum object. We have quantum centroid, and a good discrimination between quantum centroid means a high level of Elstrom bound. On the other hand, it means a good classification or high level of the accuracy. That's not all, because we can again exploit quantum foundations, let's say, or quantum information, to provide a further benefit. And this is given by the fact that, unlike the classical scenario, in the quantum one, if we provide, let's say, copies of a given status, of a given state, we provide additional information. It is not intuitive in a classical framework, but it is well known in a quantum one. So if we, instead of using the state raw that comes from an encoding, we put in place of the state raw a tensor product of raw time and time for itself, we provide an additional information. This additional information is, again, proved also experimentally. Indeed, we can see that by providing copies of each element of the data set, we again have an increasing of the accuracy. And okay, we have also and what we see at the end is that our quantum inspired classifier with copies, with this number 4, 3, 2, 1 means the number of copies, on the average overcomes all the other standard classifier. Okay, again, used over 14 data set and compared with 11 different classifiers. Okay, so okay, I prefer to move on the practical application, and okay, we apply this method also in different bioimaging purpose, with result that, again, I don't want to say that are groundbreaking, but at least very promising. I like to do this. Okay, we provide in the context of idiopathic pulmonary fibrosis for a kind of preliminary experiment, but mostly in a large side experiment in the context of clonogenic assay evaluation. And we did it in collaboration with the University of Cambridge and the Biomedical Imaging Institute of the CNR in Catania, in Sicily. Okay, so what is, okay, a clonogenic assay is a quantification technique of the survival degree of in vitro cell cultures, which is based on the ability of a single cell to grow and form a colony of cells after a given treatment. Sorry if I speak in a very trivial way about this, but it's just the idea I had of this. And the question is, after a given treatment, how many cell colonies can be individuated? So, this is the pictures, this is the kind of pictures we was dealing with, where, okay, this is, as you can see, this is considered as a colony of cells, okay? And the question, the purpose is just to counter the number of colonies, because it's very, very effective in order to prevent some disease or make also some diagnosis. It's very important. It's very important. Recent results show how, by a classification between pixel X belongs to the colony or pixel X belongs to the background, it is possible to have information about the number of the colonies. So, if we provide a good classification, pixel by pixel, for each point of this picture, we can also have a good information about the number of the colony of a given picture. Okay, so, the setup of the experiment was not a very trivial stage, because the communication between us and the people who was working biomedicine was not easy at the first glance, because we needed to decide for a common technology. Because when I say, okay, give me a vector of features, they say, what do you mean? I can understand in a plenty of different ways what you are asking me. And so that was the setup was a very interesting part of the collaboration, and also I like to say very, very, very insightful for all of us, because allows all of us to understand important things regarding the other side, and was very, 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 very long but nice. Long but, of course, not useless. Very, 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 very useful. So, in total, we have considered 4 cell lines, and each line is given by 30 different pictures. Each pictures were given by, well, thousands of pixels, and in total, we'll deal with more than 10 millions of data. So, really a large data set. And each pixel was featured not only based on the position, not only this, but also regarding other features, other medical, biomedical features. We compared the performance of our classifier, again with respect of other well-performing classifier, and what we understand at the end, what we obtained at the end, was a very nice result for us. That our classifier, that is the HQC, was ranked in the, we applied in the 4 different cases, for 4 different parts of the big picture that we analyzed. And what we will realize is that in 3/4 of these, our classifier, again, was ranked in the first 3 among the 15 classifiers we compared. So again, we thought that our classifier, we don't say it's already ready, but is very promising also for an application in biomedicine. There are many things that I can say, but I like to conclude by saying an important things. I said at the beginning that a very nice point is that this everything I showed you does not involve quantum computers, because it's only obtained by referring to classical computer, by referring all quantum information using classical computer. And the aim is just to provide a good accuracy, an increasing of accuracy. But in principle, and not only in principle, it's also possible to implement at least the test part of this in a quantum computer, because there is a well-known Newmark theorem that allows. Indeed, what we provided was a simulation of the test part of this classifier in a quantum computer, in the IBM quantum computer. And again, the results was really close to the expected one. It means something that for us is very promising, very important, and that is the end of the talk. That is, in principle, by appealing to quantum information, but by using also quantum computation, we can put together two benefits. First, increase the accuracy, but the second, increase also the speed up of the computation. So not only speed up, but also accuracy, both together. And this is the end. But, okay, of course, walk us to the point. Thank you.
Thank you, Giuseppe, for your talk. So we have 5, maybe more, few more minutes for questions. Yes? Oh, okay.
What are the limitations for running this application on quantum computers? Is the depth of the circuit, number of qubits, or anything else?
Yeah. Thank you, Luigi. Yes, there are strong limitations. Basically, what I show you here by this circuit is a very toy model, because it's given by a short data set, given only 2 features and 2 classes. And as you can see, the circuit is already not too long, but long enough. But the most important point is that this circuit is able to represent only the test part, not the training. The training is the most consuming part of the algorithm, and actually we don't have the quantum algorithm that is able to provide the training part of our quantum-inspired classifier. This is a challenging. I invite all of you to collaborate with us in order to find, let's say, an optimal circuit that could be able to provide not only in the test, but also the training part. We can also consider that, as can happen very often, at this moment we can consider also emerging between classical and quantum computation and have some kind of hybrid result. At the moment we can also be satisfied with this. But at the moment it's a good question. It's, the application has some limitation. Yeah.
I have a very quick question, but just going back to the foundation. But let's assume that you have just a 2-class problem, okay? And you know that the 2 class are, the probability is Gaussian, so there is Gaussian noise. So what my point is, in this case, how can you say that there is a superiority of using the quantum model? Because we know that if you have a random noise, and more or less you know which kind of random noise you have, the optimal discrimination theory is the statistical one.
Yeah, I see. It is a very good question. Basically, in principle, we don't know. In principle, of course, we cannot say this. The point is that what we consider is that this quantum-inspired algorithm is given by the fact that I answer again in a more, let's say, foundational way. By using the quantum centroid, we pick some kind of information that generally is not considered by any kind of classical topology, even the Gaussian one. So, but we don't know that we don't say that it's superior. We say it's something that is completely different with respect to any classical one. Maybe there is something more, maybe for some data set there will be something less. But generally, okay, let's say that the quantum information protocol is just thought in order to pick more information from from data set. Yeah.
So you are telling in short that you are able to capture the kind of uncertainty that is this.
Exactly. You read exactly the correct word, uncertainty. Yes, that's exactly this.
Yeah, what I learned now again from your talk and also in the cooperation with Roberto in Munich is that your approach and your use of the quantum formalism is in some sense independent on the advantages of quantum technology. That means in a more general term, what you are doing is mathematical physics. Mathematical physics is different from theoretical physics. Mathematical physics means you use the mathematical which is known in application in physics, for example, for socio-economic systems. And so you are using now the quantum formalism in competition with classical approaches. Because his backstroke classifier was in a competition with classical classifiers. And for me, historically, it is amazing that these ideas of the backstroke classifier came up in the 70s. Yeah. That was the time of Marisa and the time of Peter Mittelstädt, when these early ideas of quantum logic came up in philosophy, in logic, and so on. And nowadays, we see that there are even very successful instruments, perhaps, for applications in medicine. And that is amazing, but it is a main point for the strategy of your approach in the future. You do not depend on the technology advantages for a far away realization of the quantum computer. But here and now, the quantum formalism is very interesting and promising for this kind of application.
But we can discuss of fragments.
Thank you very much for this remark, because it's also related to the previous one. Basically, the quantum physicist was asked in the past to modeling uncertainty, even before speaking about the implementation in quantum
data set, and to share this data set as a reference and a common basis for doing the same kind of experiments. And there was an explosion of this benchmark data set, and in the end, after 10 or 15 years, was not more possible anymore to publish a single paper in AI if you don't use this data set. And as you can see, there was a trend so that this benchmark data set, they became larger and larger year after year. This is important for our story because this was the beginning of the idea in AI that if I collect enough data, I can really solve real problems. Yeah? I can represent the physical world collecting data so well that even if I don't understand the physical laws, I can solve the problem. And this was the idea of data-driven AI, And for some application, this kind of paradigm, this kind of philosophy was beneficial, really beneficial. For example, for the technology that we call optical character recognition, that is the tool that now I can take a picture of any written document, I can scan it and translate it into a Word document. The increase of the number of collected data set and the size of data set was really beneficial for the advancement of this kind of technology, like optical character recognition, was really beneficial. So for some application, the idea of collecting larger and larger benchmark data set was good. This is what I call the period of machine learning of known unknowns. What does it mean, known unknowns? Known because in this kind of machine learning, I usually assume that I know the kind of objects that I want to recognize, okay? But at the same time, differently from the beginning, now in this kind of machine learning, I consider uncertainty. I consider that my data are affected by noise. So this is the reason why I refer to this kind of machine learning and AI as machine learning of known unknowns. Unknown because data are affected by noise. That usually is random, so I cannot predict exactly. I need probability, the theory of probability. And then let me come to what I call unknown unknowns so that I can explain why I'm using this terminology. Now we are in the year 2010. And inside the artificial intelligence community started to emerge, to come out, an interesting question related to this fact. You should imagine that in 2010 was more or less 30 years that people, they were collecting every year larger data set, larger benchmark data set. And the belief was that larger data set is good for creating practical tools for solving real problems. This was the mindset of AI people at that time. But in 2010, some people in the AI community started to raise this question. Are we sure that larger data set means that we are really able to solve real problems? The question was, are we sure that if I continue to collect picture of real objects, I'm really able to recognize any real object in the real world, in real condition? And this was an inspiring question for the community of AI at that time. Yeah? Because the idea at that time can be, let's say, simplified that in the AI community, we are believing that the map is the territory, but we know that is not true. Yeah? And so in 2011, these two guys, Antonio Torralba and Alexei Hefros, one is a Spanish guy, the other is, if I remember well, is a Polish guy. Well, they wrote a very influential paper, with a basic question. What is the value of current data set? I mean, the benchmark data set that everyone is using, that are a must for publishing any paper. What is the value for the final goal to create really a product that can work and can work well in the real condition, in the real world? So the idea was, are we sure that the data set that we use for writing scientific papers are really useful for creating practical solution in the real world? And the answer, unfortunately, was, well, the data set that we use for writing scientific papers are, let's say, better than nothing, but not very useful. Why? Because they discovered what today we call the problem of biased data set. What they discovered is a very simple fact. They discovered that, unfortunately, the benchmark data set that the scientific community was collecting over the last 20 years, they were very biased. What does it mean, very biased? Have a look of that picture. And that was a stupid discovery, a little bit trivial, that was done some years ago, that someone did some experiment using the best image recognition algorithm provided by Google, and checked that this tool was very good in recognizing cows when the cow is over a green background. But when the cow is on the sand, on the beach, it fails. And of course, the answer is very trivial, because the training data used, for the majority of the times, they contain cows over a green background. And this can appear from a scientific viewpoint really a trivial discovery, but it's a true story. It's a true story. And the problem is what today we call the problem of biased data set. Of course, you could say, well, it's very simple. The solution is let's collect more picture of the cows in different conditions. But unfortunately, sometimes it's very difficult because collecting data costs a lot of money and time. Okay, and well, this is clear with ChatGPT. Of course, when ChatGPT is failing, sometimes it's due to the fact that the training data have been collected without checking the problem. Okay, why? Because it costs too much. Yeah? It's much better to collect data without doing any check of potential biases. Okay, said that. Well, the community of AI, after this discovery, they start a large debate, telling someone in the community said, okay, but the problem is that our data set are too small. We should increase. We should increase, and we can solve the problem of bias if we increase the data set. And there was a strong debate inside the community. Some people, like my friend Theo Pavlidis, said, no, forget that increasing the data size is the solution, because let's consider images. It's impossible to collect a number of images so large that you can represent all the possible variations. It's impossible. This was an opinion quite influential, telling, no, the solution is not increasing the data set. You should go back to the fundamental, as Professor Mainzer said. You should go back to the fundamentals and think about a different direction, not just collecting more data. Other people, however, they said, no, this is not true. There are some applications like natural language processing, for which we do believe that if you collect more data, you can solve the problem, the real problem. This was a gentleman, well, researchers in Google. This guy in Google, they are very smart, of course, and in particular Peter Norvig, that was the chief scientist in Google, he said, no. Consider natural language processing. When I want to create a computer that is able to conversate with humans so well that it can pass the Turing test. And Peter Norvig said, if I collect enough data, if I read all the books available on the internet, I'm confident that I can create a computer that is able to conversate with humans, and you cannot distinguish from a person, a real person. And I don't need any real knowledge of human language. I only need to collect data. That's enough, okay? And indeed, in a retrospective way, this was intuition behind the future success of ChatGPT. Yeah? Because you should imagine that before this, let's say, strong statement of Google, people was thinking that for developing a chatbot like ChatGPT able to conversate with humans, a must was to have a clear modeling of human language. Create a model of human language, not just learning from data. The intuition was, no, it's enough that I collect a lot of data and I become able to predict the next word in a sentence. This is enough. This is enough. That was the intuition. It was a brilliant intuition, indeed, in a retrospective way. And this was the start of the success of AI, year after year, to reach, for some application, the point that machine learning is better than humans. Yeah, for some applications, not for any application, but for some application, the performance is, in terms of accuracy of AI based on machine learning, is better than humans. For example, in image recognition, well, today we reached the point that machine learning is better than humans. When you have to recognize millions of objects in millions and millions of images, machine learning is better. Why is better? Because you know our human visual system is super good. It's super good. And we all are able to recognize any kind of object in many different situations. But suppose that the objects are familiar to us. If I see an object that I never seen, I don't know. Machine learning can be trained on millions and millions of objects that I never seen. And so it's better than me in that sense, okay? And so today we know that the performances of machine learning, AI, is better, is superhuman for some application. The accuracy is very, very good. But 10 years ago, in different laboratories in the world, including a laboratory here in Cagliari, some people started to think about, okay, but high accuracy means that machine learning is also robust. What does it mean, robust? If while the images or the data or speech is changed in some way, the performance is still good. How much is robust machine learning? High accuracy means that you also have high robustness. What happens if I take a picture, a digital image, and I change slightly the image? The performance is still good. And around 10 years ago, in different research laboratories in the world, including here in Cagliari, we tried to do this experiment. Let's consider these two pictures. They look the same, of course. And believe me, they are almost the same. They are so small changes that we are not able to distinguish. There are a few changes, but it's very difficult. And the idea was, what happens to a machine learning algorithm? Is able to recognize that they are clearly the same object. To tell you the entire story, the idea that we had in Cagliari and in other places was, let's understand how much I have to change an image of a school bus so that machine learning wrongly recognize the image. And our intuition was wrong, was that I have to change a lot. I have to change a lot the image. But in the end, we discovered a strange thing. We found a mathematical algorithm, quite simple, in order to find some small changes in the image that if you do this perturbation that is very small, and of course it's not a random perturbation, it's a perturbation that you find solving that minimization problem. So you solve again a minimization problem. Machine learning, the mathematical basis is minimization, nothing else. Minimization with constraints, to say. We discovered that the recognition result of machine learning is completely wrong, even if the changes, the perturbation is very, very small. Of course, the perturbation is not random, yeah? It's a perturbation that is the solution of a mathematical problem. But, well, what does it mean, this? This means that machine learning is not very robust. From the mathematical viewpoint, is very sensitive to small perturbation. It's very sensitive. The mathematical function behind is not very stable. It's quite sensitive to small perturbation. This is what I call unknown unknowns, yeah? Because it's not just noise, yeah? It's also that you have some data that you never seen. It's completely unknown. And this is the reason why machine learning is not very good with this kind of things. Why machine learning is so, let's say, within brackets, fragile? Fragile means I change something very little, and the prediction of machine learning is completely wrong. Why is so fragile? Again, as Professor Mainzer said, it's useful going back to the fundamental, yeah, to try the explanation. One explanation is very simple. Machine learning is very fragile because as this German guy, Bernard Scholkoff, yeah, in Tübingen said some years ago, when I discussed with Professor Scholkoff this problem, the answer was very simple. He said, well, of course it's very fragile, because the basic theoretical assumption behind machine learning is the assumption that in statistics we call IID, identical, independent, distributed data. And this is the assumption behind machine learning. That means that we are assuming that the training data are representative of future data that we don't know. It's the same assumption that we do with a lot of failures in finance and economics. Yeah? But in finance and economics, we know that is false, and so usually when you invest your money, well, by law, the bank is obliged to say you, be careful that future returns, past returns of your investment is not representative of future returns, okay, because the market is completely random. Okay. But in machine learning, we forgot this. Yeah, we forgot this. Yeah, because also finance is based on the high ID assumption, of course. So the success of modern AI is for tasks for which we collected enough representative training data. Yeah, because nobody can predict the future if the future is different from the past. It's quite easy to understand. I cannot predict the future if there is some, let's say, black swans. Yeah, something that I never seen. Yeah, unknown unknowns, as Professor Scholkoff said, points exactly this lack of robustness that came from this basic assumption. From this basic assumption. Of course, you can say, well, let's develop a machine learning theory that is not based on this assumption. Oh, we tried, but we failed. Yeah, we failed in machine learning, we failed in finance, and so yes, it's quite difficult, okay? The other problem is biased data sets. Biased data set is the curse of AI. If your data set is biased, yeah, no way. But unfortunately, creating non-biased data set costs a lot of money and time, and sometimes it's impossible. Imagine ChatGPT has been trained using Wikipedia, using all the digital books available. How can you check that they are not biased? How can you check? It's really impossible. And it costs too much. It costs too much, okay? When you use ChatGPT, the so-called large language model, this issue of bias is so strong that people are using another name, hallucination. Hallucination, okay? Good, I'm going to finish. Which way we have taken from the beginning to modern AI? Which way we have taken? Why we left the road of the fathers? Because in the minds of the fathers, the idea was different. Try to understand well how brain works, trying to create a model of human language, and then let's simulate inside computers. Why we left this idea? You remember Claude Shannon, Ross Chester, Manvin Miskin, they were genius. Why we left this way? Because it didn't work. Very simple. It didn't work. We spent a lot of money, but it didn't work. And which way we have taken? We've taken a shortcut. We have taken a shortcut. What is the shortcut? The shortcut is that at a given time, we stopped to try to model physical phenomena or to understand well how the physical world or human language can be modeled, and we decide to use just learning, statistical learning from data, just to find the statistical correlation. Statistical correlation. Machine learning is statistical correlation. Machine learning is not understanding that this is a human face, this is a cat. It's just discovering that there are some specific patterns, and you have a statistical correlation with high probability. With high probability, yeah? That is the point. So today, ChatGPT is almost within brackets, intelligence according to the Turing test. It's quite difficult for many conversations to distinguish that is not a human, okay? But yeah, we should remember that is not learning in a human way. It's learning statistical correlation between data. Yeah? This means that modern AI that is based on the so-called thinking fast paradigm, using the words of a very famous Nobel Prize, Daniel Kahneman, Nobel Prize in economics, can exhibit a lack of robustness at several risks. What is the lack of robustness? That if the cow is on the green background, it's okay. If on the sand, it's not okay. Okay. Maybe this limitation will be solved by future AI systems, which are more able to reason. And indeed, you know, if you use ChatGPT or Claude or other large language model, over the last month, you have the option to ask to ChatGPT, think about the step, reason. And try to think in a more slow way. So slow and fast thinking. Thank you very much for your attention.
Thank you, Fabio. So questions, first one, then, and then, okay.
So, thank you very, very much. It was very nice, at least for an ignorant as myself. No, my question can be maybe provocative. I'm a logician, so it's nice to see that everything started with logic somehow. In your opinion, do you think there is space for this formal logic in modern AI, or everything goes down to big data and statistical methods? Thanks.
Yeah, it's a good question, and the short answer is yes. There is room, there is space, and indeed there are an increasing number of papers trying to exploit logic, in the sense that the big challenge now is how can give to AI, for example, to ChatGPT, a model of the physical world, or anyway, additional knowledge about how the world is working. And there is a new stream of work that is trying to express, for some specific knowledge that can be expressed well in logical form, they try to use that. Yeah. For example, we did it here in Cagliari. We did some work, and also in Genova. I have double affiliation with Genova and Cagliari. We did some work just to avoid the problem that the school bus is misrecognized as an animal. We use a domain knowledge expressed in logic form, for standard, and then but what is the technical problem? You have to transform first order logic rules expression in a way that can be embedded inside the mathematical not equation, the loss, so-called loss function, that is a minimization, is a function that you have to minimize. The problem is that you have to take logic and put inside a mathematical expression that is the loss function. And make it continuous, exactly, so that you can minimize using gradient descent. We can discuss off the records. Thank you.
Thank you for this wonderful talk. And my question is the following one. I think when coming to the large language model, it's a very simple model. I'm coming back to cancer. A single cancer cell is composed by about 50,000 proteins. So theoretically, we can assume that all those 50,000 proteins have a distinct function. But the number of functions is much higher because all those proteins can cooperate. So theoretically, it's a number of 50,000 to 50,000, which means it's a number, I think, much higher than the molecules of the universe. So how would you like to handle this unknown? And would you like to come to know this?
Yeah. No, but you are completely right. Well, I'm not advocating that any, let's say, artifact, I mean, a device can really manage all the possible uncertainty and the unknown unknowns, okay? This is not possible, and the natural evolution showed that is not very useful. Yeah, you have to predict what is useful for survival, not everything that can happen in the future, okay? That is true. Well, probably more linked to your comment is the fact that while there are some researchers in the community that are telling, yes, it's true, ChatGPT is in some sense limited, it's just learning statistical correlation, but like in biology, it's composed by many small building blocks, and we believe that there is an emergent capability that is more than the single component. Yeah. So there are some people that they say, yes, ChatGPT is not doesn't know Italian grammar, but in the long run, probably it will develop a sort of grammar comprehension inside. Given that you have a lot, it's the same way that probably is what scientists call emergent intelligence. Yeah. You are not able to understand why, but probably there is an emergent intelligence, like in the evolution. Yeah, you have many single components.
Is that possible? No? Should I stand up?
You can speak from there.
Okay. No. Okay. Two remarks concerning the fundamentals. These are, of course, crucial. And connecting it with some questions. First, you mentioned Schulkopf from Tübingen, and what we are doing there is just the next step. After big data and statistical learning, and you highlighted in the end of your talk, it's all statistical correlation, like in medicine. You have a lot of data and it is statistics, nothing else. So the idea came up, you mentioned it on your last slide, concerning causal thinking, because not only there is some probability for a statistical correlation of a tumor, but what is a tumor? And what is the causal, and what the causal model? And that is the idea here. Of Schulkopf, that means with very few data, science, physics was very successful. Newton, Einstein, they had a causal model. So the idea is, and that is now made at the Max Planck Institute in Tübingen, to find algorithms, not the general relativity and gravitational theory, but for a special situation, the assumption of a causal model for explaining the situation. Are there causal algorithms? That is a great idea here. And the next concerns logic. A great idea for AI, machine learning, nowadays is the classical verification problem. Because in classical software, logic came in with a verification problem. That means algorithms which are well known by Hilbert and Gödel and so on to control logical formalism. And then the idea, let us control a software program. And now the idea, is that possible for these big data data situation, verification of machine learning algorithms, because without that we are running into great problems concerning trust in AI. So logic again is very, very important, together with causal learning.
Yeah, I do agree. I do agree. And indeed, of course, in Tübingen, Professor Scholkopf and his institute, they are doing an amazing job in trying to move to another direction. So not just learning statistical correlation, but creating a causal model. Yeah, and probably is a very promising direction. Yeah. Another direction is how to embed inside machine learning knowledge, different kind of knowledge expressed in formal logic or in other way. Unfortunately, but this is my comment, the problem is how is so brave to invest a lot of money, yeah, so that you can push this direction, given that the business model now is more about collecting more data, using more computational power, and there is a potential short-term financial return. Yeah, the other is of course much more risky. Yeah, and so and especially because ChatGPT is working, it's working. So if you simply say, well, it's working well, but I have another idea, okay, but it's not easy. Meta, the Meta company is trying, but just for a commercial marketing strategy, to say there is another way, but simply because they failed to do it this way.
Just one more question.
Thank you for a fantastic talk. A very, very quick question. Sure. Curiosity, by the way. I understand the fact that to create an unbiased data set is very expensive, but in some particular context that we already know, is it possible to increase the training data set artificially? I think that just echo.
Yeah.
Echo in the same.
No. Yeah. The short answer is yes. In AI, it's called data augmentation. Yeah, data augmentation. You take the data that you have, and you can create new data. Yeah, representing the cow in different situations. Yeah, you should be careful because you are not sure that you are creating real data, but and yeah, in some cases it's possible. Data augmentation. Yes, in general, bias is an issue that you can solve only if you have a causal model. You have a model of cause effect. Okay, think about finance. Bias is a big issue in finance. They never solve it because it's too hard. But in that case, it's different because the financial market is a random walk. So there is no way.
Thank you very much. And so now we have the lunch break in the same location as the coffee break.